Today's video, we will learn everything you'll need to know about condensation, retrosynthesis, and synthesis of, and the different types of dicarbonyls that there are. And this is very important because it is through identifying the type of dicarbonyl that you're able to understand what the initial reactants were. So this is a beta ketoester because there is a ester on the beta carbon. The alpha carbon is the carbon right beside the carbonyl. And by the way, condensation means combining two carbonyls into one molecule. And here we combine two esters because it's a beta ketoester under the Claisen reaction, which involves the first step as a deprotonating source, NaOET, could be NaOMe as well, depending on what your ester is, followed by acid. And a lot of these condensation reactions are reversible, but sometimes it favors a forward reaction more. Okay. The other type of dicarbonyl is a beta hydroxy carbonyl. This came from the auto reaction, which happens in base and water. Okay, but if you're at a beta hydroxycarbonyl, there is no heat added yet. Because when there is heat added, it would eliminate that alcohol group and create an alkene. So this is the auto reaction with heat. This is called an alpha beta unsaturated carbonyl, because the alkene is between the alpha and the beta carbon. Here we have a dicarbonyl, but it's not an ester, nor hydroxy, nor an unsaturated. So with a regular carbonyl then, dicarbonyl, we can say that this is a cross between the auto and Claisen, or other words, this is from a ketone or aldehyde plus an ester. And because there's an ester, the reaction conditions here will be the same as that of the Claisen reaction. If there is a 1,5 dicarbonyl, 1, 2, 3, 4, 5, this came from the METHYL addition, which is a reaction between an alpha beta unsaturated compound, the conjugated system here, with some sort of ketone or aldehyde. So this happens in the same reaction conditions as the auto reaction. Okay, sometimes they will throw you off by adding extra things on this dicarbonyl. So let's say something like this. But at the end of the day, it's still a 1,5 dicarbonyl. Okay. Now let's think about retrosynthesis. How do we make these dicarbonyls? Also, there is one more. It's a Robinson annulation, but I have another video on that with retrosynthesis and synthesis of. So retrosynthesis, there is one commonality between all these, and it is add hydrogen on the alpha carbon, but the beta carbon is where things vary. So let's start with the Claisen. It's one of the trickier ones. Although the ester is on the beta carbon, there's also another beta carbon here. And because we want to make sure that the reactants of both, the starting reactants in Claisen are both esters, so that's why we want to think about the ester, putting the ester on the beta carbon instead of putting it on the alpha carbon, which already has an ester. So how this might come about is, let's draw the alpha carbon side. So it's a side with the ester already. So then we just put some hydrogens here. And now for the beta side, this is a beta carbon. Now I'm gonna add an ester to the beta carbon. Okay, so Clayson, add ester to beta carbon. For the autoreaction, we will draw our alpha carbon. This is our alpha and this is our beta. But for the beta carbon, it will now be replaced by a carbonyl. So this side must be an H then. But let's say we have an auto product in heat. So we draw the alpha side. Now the beta, instead of the alkene there, I'm going to replace it with carbonyl. Okay, so far for Clayson, the beta carbon becomes the ester. For auto reactions, the beta carbon becomes the carbonyl. But here, we can call this alpha, we can call this beta. We draw the alpha side. We replace that, we add hydrogens on the alpha carbon, but for the beta carbon, we will add an ester. Okay. So this is a little bit of a special case scenario. When you have just a dicarbonyl with none of these special groups, then you know it comes from a ketone and an ester. And for the METHYL addition, sometimes there are multiple options. So this can be our alpha, this can be our beta. So we redraw the alpha side. And the alpha carbon gets some hydrogens. Whereas for the beta side, we will add an alkene between the alpha and the beta, like that. Okay, so that's retrosynthesis. But now with these products, with these special dicarbonyls, they can undergo further reactions as well. So for all of these, they have one thing in common, is that they all have an alpha carbon. And that alpha carbon can be deprotonated via LDA and THF in -78 degrees, or if you're dealing with esters, such as beta-keto esters or diethyl malanates, you should use an AOET as a deprotonating source. Once you deprotonate these alpha carbons, which will put a negative charge here, they can undergo SN2 reactions with alkyl halides. So that will add, so it will look like this. So we start with, let's say here we'll do a diethyl malanate or dimethyl malanate if we put ET here. So we deprotonate this, but we would change ET to ME here. Deprotonate, so that gives us a negative charge, and we do SN2, so that will alkylate here. Okay, so that works for all of these things. Whereas for the unsaturated ones, it's a little special. We can do an addition on the beta carbon. Addition on the beta carbon with some sort of nucleophile, or let's say could be an HME. So this one's just a little special. We will do addition, nucleophilic addition, and on the beta carbon. Okay, anything else special here? But yeah, this is important for alpha carbons. Okay, now there is something really important here, is that for these esters, so these are the VIPs, here there is one ester. This is an acetoacetic ester synthesis reactant. So that means after doing these two steps, if we put it in some base, water, heat is later, heat, but here there's an acid as well. So this is only for the esters. If we do that, that will convert your OET into O minus and get protonated by the acid into OH, and then that OH get decarboxylated. So the COOH in heat will take that COOH away. So with this first one, the acetoacetic ester synthesis, it will create a ketone product after putting it through these final steps. Whereas for this diethyl malanates, putting it through these last steps will yield a carboxylic acid. But if there isn't these two steps, then do not do that, then just add the alkyl groups on the alpha carbon.